Okay, so we just take off from where we had left in the last class. We had derived equation 7.18, which was the equilibrium of the forces. So I will just write out that equation as we had. A1, and if you look at this figure, you will see what A1 is. Okay, it's this entire area, and it would be sigma x. So we had done this discussion in the last class. Minus delta fyx. We had also said why delta fyx would act. Okay, and okay, so this was at x. So this particular term is on this face, this particular term is on this face. Okay, or a delta x wherever delta x face. Okay, so this is what we had done, and then the integrations are taken over the shaded area over here, a1, and it goes from y equal to y1 to y equal to c. So this is where this element lies right now, y1, and the maximum it can go is to c. Okay, so now we substitute 7.16 into this 7.18. So do we have 7.16? Yeah, this is 7.16. So sigma x equal to minus mby divided by izz. So we want to put this over there. Okay, so we will put sigma x according to 7.16, and then we would get, sorry, we would get delta f, sorry, delta f yx is equal to minus of a1 into mb plus delta mb y by izz dA plus a1 mby by izz dA. And this, if you like, minus b and plus mb will cancel, plus mb and minus mb, so you would be left out at minus delta mb by izz into a1 yda. Okay, now if you divide both sides by delta x in this equation, you divide both sides by delta x, you would be able to write delta fyx by delta x, and then this would be equal to minus delta mb by delta x by 1 by izz a1 yda. Okay, now you take a limit of delta x tending to 0, and then you would be able to write it as d fyx by dx equal to minus minus dmb by dx by izz a1 yda. Sorry, I'll just, okay. Now if you go back to equation 3.12 in your textbook, let's go back to 3.2 in the textbook and see what that was. Yes, so it was this section 3.5 in which you had the differential equilibrium relations, and the equations were dv by dx plus q is equal to 0 and dmb by dx plus v is equal to 0. Okay, and if you remember, v was the shear force which was acting on this differential area. The other side of the differential area had a v plus delta v shear force. Okay, now we want to make this substitution in this one. Okay, so we can write from this one we can write dmb by dx is equal to minus v. Now this particular thing must be kept over here, and that would mean that dfyx by dx is equal to v by izz, and so just let's write as v of x. Okay, just to be clear that it varies with x. Okay. And it's obvious, right? I mean, it varies with x and only with x, right? That's why you don't have a partial derivative, and the same happens for mb as well. It varies with x and only x. Okay, so this is what you get, and if you would want to write this particular term as a q yx, then you can write and this as q. Okay, so you can have more concise form, which is vq by izz, and it is very easy to see what these terms are. So qyx is the total longitudinal shear force transmitted across the plane defined by y equal to y1, this particular plane, sorry, this particular plane, the plane which is below over here. So that is the total the quantity qyx, which is the total longitudinal shear force transmitted across the plane y equal to y1 per unit length along the beam, and it is called shear flow. Okay, and then the integral q, capital Q, is simply the first moment of shaded area. So this is the first moment, and if it was a y square, we would have called it the second moment. So it's the first moment of the shaded area A1 about the neutral surface. Okay, so once you do this, you should be able to find this equation, which is 7.23. Now if in the presence of a shear force, the bending stresses are in fact given by 716. Okay, if in the presence of a shear force, the bending stresses are in fact given by 7.16. So let's look at 7.16 was sigma x equal to minus mb, I think this one, minus mby by izz. Remember, this was an approximation for this engineering theory which we were trying to develop for stresses in a beam in the presence of shear forces. So once that is done, in the presence of shear forces, the bending stress are in fact given by this equation 716. Then 7.23 is an exact expression for the shear flow. So this is exact provided this is true. Okay, now the shear flow qyx obviously is the resultant of shear stress tau yx distributed across the width b. So this is width b, and since qyx is the force per unit length in this direction, if you divide qyx by this, you get the stress. So tau yx is essentially qyx divided by b. Okay, so our derivation gives us no information as to the nature of disturbance, but if we can make assumption that the shear stress is uniform across this beam. So this is an assumption that shear stress is uniform along the beam, then you can make this approximation, just divide it by b. Okay, and this you would be able to write as vq by bizz. So because there is a symmetry in the stress, so tau xy equal to tau yx, and it will be equal to vq by bizz. Now if you look at figure 7.13e, this particular figure, we show on the faces of the segment the nature of the shear stress distribution given by 7.25. Okay, and tau xy, if you see, is like this. I mean, these little arrows which you see over here, and tau yx are these little arrows, and tau xy are the same arrows in the x direction. The stress is constant, that's the first part, and that's why you see all the arrows are of the same same size, both on this face and this face and this face. Over here you see the arrows are of a different size because there is a variation in this figure, but in this case they are of the same size, and hence the magnitude of those is the same. Okay, so it has a constant value, and on the x faces it varies from this constant value at the bottom to 0 at the top. Okay, okay, so that's where we leave this part out. Now, the foregoing theory can be proved to be internally consistent in that it can be shown that for a beam of arbitrary cross section of the resultant of the stress distribution 7.25, this one over the cross area is in fact the shear force. So this is something which you will be able to see in problem 7.43, and you will notice that there are many problems in this textbook and which we will be doing which will require you to thoroughly know the theory. Those problems are not independent of the theory. Okay, so please keep in mind when you solve problems like this, like 7.43. Now, in summary, we have found out the bending stresses in a beam with available moment distribution. This was the distribution which we had, and on the basis of this assumption and from the consideration weekly, we found the shear flow distribution, and we finally assume the shear stress to be uniform. So please make a very good note about the approximation and assumptions which you are taking. Okay, they are very, very important. Okay, so let's see it in a slightly more specialized, under slightly more specialized conditions, and that is when you have a rectangular beam or rectangular system. Okay, so this is theoretically like some sort of another way to find the shear force distribution, and what you have studied until now was the general method. This is the specialized method. Okay, so in case you have a rectangular beam, you can use this method which we are about to discuss now, but the above method will work for any cross section as long as they satisfy the conditions which were required. Okay, so the assumption from the start is that the shear force is distributed uniformly across the width. This distribution, recall, this one, tau yx. So this is something which we made towards the end. In this derivation, we will make this assumption at the start itself, that the shear stress is distributed uniformly across the width, and the stress distribution in figure 7.14 is then a case of plane stress, and the equilibrium equations 4.13 apply. So if you look at the equilibrium equations 4.13, let's see what they were. You can check 4.13. Yes, so 4.13, if you look in your textbook, you will have this equation: dou sigma x dou x plus dou tau xy by dou y is equal to 0, and dou tau x by dou x plus dou sigma y by dou y is equal to 0. These were the equilibrium equation, and clearly they were under certain conditions. Can you recall what those conditions were? It was a two-dimensional condition, so clearly it was a plane stress condition. That's why you have the z terms missing. Okay, so the stress distribution figure for 7.40 is then a case of plane stress. So this is plane stress as we had discussed in the theory, and it's also made a note in your textbooks. Okay, so that's why we are not given a new equation number. It's exactly the same as 413 over here. Now if we deal with a case where the shear force does not vary with x, let's deal with case which shear force does not vary with x. The shear stress will also be independent of x, right? And okay, let's see. Okay, and the second of 4.13 is automatically satisfied in this particular case, since the normal stress sigma y has been assumed to be 0. If you look at figure 7, equation 7.8, equation 7.8, if you recall, where we had found out all the stresses. So that was in this. So we had said that sigma y is equal to sigma z is equal to tau y z is equal to 0. So this was assumed. And why was it assumed? Because the surfaces were having sigma y equal to 0, and since that dimension was very small for a slender beam, we assumed that sigma y would be 0 throughout. So in this equation, since this term is equal to 0, sigma y, this would mean that tau xy will also be dou tau xy dou x will be equal to 0, and this means that tau xy will be independent of x. Okay, and this basically the fact that this is coming independent of x is also that if the shear stress V is constant, then tau xy will also be independent of x, and hence this equation is satisfied. Okay, so you are basically starting from the left hand side. Call this 0, this was 0, this was independent of x because V of x was independent of x, hence it is equal to 0 and equal to the RHS, and that's why they say that the second of this is satisfied. Now substitute 7.16, this was 7.16, 7.16 into this one. So you would want to write dou tau xy by dou y minus is equal to dou by dou x. What is sigma x? It is mb minus mb y by I z z. This is equal to v y by I z z. Okay, so after you substitute this 7.16, this one over here in the first of this equilibrium equation, you get this particular term, which is 7.26 in your textbook. Now we want to integrate this so that we can have this value. You want to integrate it again from the level y is equal to y1, where tau xy is to be evaluated, to the level y is equal to h by 2. So this is y equal to y1, where this stress is acting. So this is the point of interest over here. Okay, and then h by 2 is the total half thickness of this half height of this rectangular beam. Okay, so in the earlier case you know that this was a c in total. Okay, so this c is now h by 2. So okay, so this is the top surface, and that would you would carry out that integration, and you would finally get minus you would get minus of tau xy with the limits y1 as h by 2 is equal to v by I z z. This is y square by 2 h by 2 and y1. Now we have to put in these limits. This integration ends, and because there is no shear stress on the exposed top surface, remember there was no shear stress on this top surface. Okay, and that is why the comment was made that tau xy is tau yx is 0 on this surface, and the same would be happening on this top surface as well. So tau xy or tau yx at the top surface is 0. So at h by 2 that value is 0. Okay, and then you will take tau xy 0 as at y equal to h by 2, and then when you substitute the limits you should get tau xy is equal to v by 2 izz, that is h by 2 whole square minus y1 square. The shear stress is, as you see, maximum at the neutral surface. Okay, so the neutral surface is shown if you see this figure 7.15. It's why is it maximum? Because y1 is 0 over there. Okay, y1 is 0, so tau xy will be maximum, and it falls off parabolically as illustrated in 7.15. This is how this tau xy varies. So it will be maximum over here, and as you go up it will decrease, as you go down to the surface it will decrease, and this will be parabolic behavior because you have this y square term. Okay, so this is the distribution which is shown, and we have seen that over there. And obviously tau xy is the same as tau yx at any given point, so there's no, I mean, nothing, the size of the arrows should be the same, like this arrow vertically should be the same as this arrow horizontally. Okay, obviously this arrow over here will be shorter compared to this arrow which will be longest because it's in the maximum, but within one of these small rectangles these will be of the same size. Okay, so that's something which has been done in figure 7.15. Now if we want to calculate the shear strains for this rectangular beam, how would we go about? Let's see that. So the shear stresses have been found out, and can you see how this tau xy compares with the earlier case in which the rectangular system was not taken? It was taken as 7.25 vq by bizz. So there were a lot of so v by izz is common, b is also common. Okay, so basically this is what is equivalent to, this particular thing is equivalent to 2q in 7.25. Okay, so this is what it is over there. Just check whether this is okay. I think it seems okay. Okay, now if we calculate the shear strain in a rectangular beam by substituting the stress distribution 7.27 into Hooke's law 5.2. So if you want to substitute this 7.27 into the, because now you want to find the strains, so the relationship between stress and strain is given by the Hooke's law, which is equation 5.2. Let me just check whether that is correct. So please check equation 5.2 in your textbook. Yes, so you should have like epsilon x given, epsilon y given, and so on, and then you will have it in terms of sigma y, sigma x, tau xy, tau xz, and so on. So you have all the stress components. Okay, many of them are 0 anyways, so it should be easy for you to find the strains. Now we find that the shear strain tau xy also varies parabolically. So if you look at 5.2, tau xy is essentially, sorry, gamma xy is essentially tau xy by g. Because tau xy varies parabolically for a rectangular beam, gamma xy will also vary parabolically because this is essentially the same divided by this number g. Okay, this implies that the originally plane cross sections distort in the manner illustrated in figure 7.16. So look at 7.16 very carefully. This means that this varies parabolically. Now how do you visualize this strain? So the tau xy, which was basically this, okay, let's just see this one. Okay, this dashed line is the undeformed one. So the strain varies parabolically, and hence this will be less, and it will keep on increasing parabolically. Okay, and the same would apply over here. So the surface which was originally plane is now distorted, and let's see how we can see and this is different from when we didn't have the shear forces. Please go back to the section when we didn't have shear forces in bending. In that case, the plane sections will continue to remain plane, but here they are distorted. Okay, so we note that if shear force is constant along the length of the beam, any longitudinal line ij does not change its length as it deforms into position I1, J1. So ij, okay, even after this distortion, I1, J1 would be of the same length as was ij. This would be there if v of x is constant, present but constant, and clearly not 0. Alright, if it was 0, then all that discussion we have already done before. So every time I say Vx is equal to constant, it's clearly independent of x but not 0. So we note that if shear force is constant along the length of the beam, any longitudinal line ij does not change its length as it deforms into the position ij. The reason for that is quite simple. I mean, this particular point has deformed by a certain value, okay, and that value you can find out. That value clearly depends on the height of this, right, from over here, because you substitute this into this, so it varies on the height, not on x. And say this point as well would also be moving in some direction like this. So the shear terms will all be, shear strains will all be moving in this form, and hence they will be all moving by the same amount, and hence ij and the length of I1, J1 will be the same after deformation. Positions are changing, but they are all changing with the same amount. So from this we would suppose that the presence of a constant shear force would have little effect on the bending stress distribution 716. So sigma x was equal to what, minus mb y by izz, if I am not mistaken. This was 7.16. Okay, so from this we would suppose that the presence of a constant shear force would have little effect on the bending stress distribution 716. How do you conclude from this that the stress will have the constant shear force will have little effect on the bending stress distribution? Why do we say that? So sigma x is equal. This is in fact the case. The exact solution from the theory of elasticity shows that 7.14, 7.16 are still correct when there is a constant shear force. Okay, so this is something we'll have to think about, that the fact that ij and I1, J1 are of the same length when v of x is constant, this normal stress should be this, even in this presence, even in the presence of this. Why would that be true? I think the reason is that I think the reason is that line element. Yes, so if you have a line element of this form, even after deformation, say along the same x direction, it would remain of the same length, and hence the strain in that direction would be 0, and because the strain in that direction is 0, the stress due to this will also be 0, and hence there would be no difference in the shear in the normal stress due to bending when the Vx is constant. So that's the reason. So you have to see this from the Hooke's law. Look at the formula of epsilon x and see how is it related to the other stress terms. Many of those terms will be 0, and this is how you can say, because the I1 I and j are of the same length as I1 j1, the normal strain in the x direction should be 0, and hence the normal stress due to the presence of, so this is due to the presence of the shear force, and hence there's no extra contribution to this. And this formula can exact be proven from the more advanced theory of elasticity as it mentioned in your textbook. So when a shear force is constant, this is what you get even in the advanced elasticity theory. So this was actually correct for V of x equal to constant, not equal to 0. Okay. So what we had assumed at the start was correct for this case. Okay. Now, as stated previously, this proof perhaps you will see only when you do an advanced course in elasticities, not now. As stated previously, this means that the expression 7.23 for shear flow is also exact for the case of constant shear force. Okay, so that would also apply. I mean, we have done it for a rectangular beam, but even when the cross section was not different, that would still be true. So both 7.14 and 7.16 are error when the shear force varies along the length. So this is not valid when v of x is a function of x, okay, and not constant. That is obvious. But the magnitude of error is small for long slender beams, and 7.23 is a good estimate even in the presence of varying shear force. So the author says that even when you do have a varying shear force, the error which this has, so this is exact, okay, actually correct and exactly correct, okay, in this case, but approximately correct in this particular case. So thus at each section of a beam in the engineering theory of elastic strains which we have studied, we take the bending stress to be distributed accordingly to 7.6, 7.16, and the transverse stresses to be distributed according to 7.25. Okay, independently of how mbx and vx vary along the length of the beam. So that's a very powerful idea. Okay, that the due to bending in, so this is sort of a summary in engineering theory of bending stress. The stresses are sigma x is equal to minus mb by y I z z, and tau xy equal to tau yx is equal to vq by bizz. This is true for v of x equal to constant exactly, and it is also true for v of x is not a constant approximately. So we use this formula either way. Okay, this is a summary of what we have done until now. Okay, so let's also look at I-beam. Okay, so it would have been unfair just to use the effort of this complicated geometry in only a rectangular beam. So we try to apply this also for an I-beam, and this will give us the confidence that we can use any shape, like even the H-beam, for example. Okay, so Let's see. So if we examine the I-beam in figure 7.17, we gain further insight into the shear stress distribution in the beams. And in figure 7.17b, we show a small segment which has been cut from the top flange of a vertical section. So this is the top flange. Okay, and this is how we apply. So we see that there must be a shear force delta fzx, okay, on the positive z face. So we are now referring to the positive z face, this face, okay, in the x direction. And if we carry through an analysis similar to what we have done in 7.23, we will be able to obtain a shear flow for this case as well. Now, one thing which you all are requested to do is to actually derive this. Please don't like mentally try to derive this, but derive this in reality. Okay, so you should do this derivation and find out that the shear flow on the z positive z face is vzq is equal to minus vq by I zz, where q is the first moment of shaded area, okay, this one y, and this is delta a. So if we make the assumption that the shear stress is uniform across the thickness T1, okay, you see how the directions are changing. Earlier it was B, here it is T1. So then tau xz will be equal to tau zx is equal to qzx. Okay, and this you would get as vq minus T1 by izz. And you would be able to get a stress distribution for the shear forces as is shown in the figure. So again, please do not skip over I-beam. You must repeat the same analysis which we have done. We have done for a general case, we have done for an rectangular beam. Please repeat the same exact analysis, word by word, line by line, argument by argument, to be able to do this analysis for a I-shaped beam. Okay, this is the only way you will be able to confirm that you have actually understood the earlier derivations and the assumptions and approximations involved. That's the single most important point. Like you may meet an engineering situation in which one of those assumptions is not valid. For example, the beam is actually not slender. Okay, the dimensions of the beam are such that not slender. So what are all the assumptions which would not be valid in that case? Okay, so this is how you have to really develop your understanding of this particular subject. Okay, so let's now move to the one of the problems, which is 7.3. So in making the brass beam of figure 7.18a, this is a brass beam. The box sections are soldered to the 1 centimeter plate. Okay, so this is the 1 centimeter plate as indicated in figure 7.18b. Okay, if the shear stress in the solder is not to exceed 1000 Newton per centimeter square, okay, this is like from coming from the design perspective that the shear stress should not exceed this value. Perhaps it is the risk, it will be at the risk of failure at this stress. What is the maximum shear force which the beam can carry? Okay, So first thing, you have to look for a picture or a video of a soldering joint. You should know what this joint is. Okay, so please look up on the internet what this joint is. I mean, don't try to solve a problem in this subject without actually seeing it physically. Okay, even in the sense in reality on your computer. uh, because this is not a physics problem which we do earlier, or perhaps even your mechanics APL 100 was taking you from school towards engineering, and hence it was fine to just like not know what it was and then still be able to apply the force balance and moment balance and solve the problem. No, it cannot be done like this anymore. So please physically see it, visually understand it, what it is. Then you see the actual problem, then idealize it. Okay, don't idealize without understanding what it is. It was fine until now, but not anymore. Okay, so this particular soldered joint has to carry a unbalanced bending moment stress acting over the cross sectional area of the box, which is shown in this figure. Okay, so we have taken this part. This is the solder over here. Okay, and the other dimensions are given to you. And if you just look at this figure 7.18c, you will have this situation in which okay, so one of the things is, I hope you can see why it is 13 centimeter. It is 10 centimeters to over here, and then there is half centimeter. So this 10 centimeter is to the middle of it. Then there is half centimeter over here, and then 2.5 centimeter to the center. That's why it is 13 centimeters. So these dimensions have to be very clear. Now, assuming that the shear flow is equal in each solder joint, the shear flow QZX in each joint is given by 7.28. So if you look at 7.28, we had found out that QZX was equal to minus VQ by IZZ, and so Q is the first moment of the shaded region about the Z axis, and IZZ is the polar moment, which you already know. If we approximate this area by the complete square annulus, you have to find what the value of Q is. Okay, and then you should be able to find this. Now there is a factor of 2 over here. Why is that there? I mean, think of why this factor of 2 is here. I mean, there are 2 joints in total. Okay, so why is there a factor of 2? Why is it not divided by 2? Okay, or why is it not just 1? So please think about this when you are seeing this problem. Okay, and then the one other problem which we can just go through simply is 7.14. Okay, and in this one you have a rectangular beam, quite simple. Okay, the formulas are much easier in a rectangular beam, and is carried on simple supported and subjected to a central load. This is the central load. We wish to find the ratio of maximum shear stress tau y xy max to the maximum bending stress. So you want to find tau xy max divided by sigma x. Okay, so one of the first notes which is made, there's these two maximum actually don't happen on the same point on this beam. Okay, because the maximum shear stress occurs at the neutral axis. Okay, we know that the maximum shear stress acts at the neutral axis, but the same is not true for sigma x max. It clearly acts at a y value. Okay, so in this case you would have to now write separately. So the maximum bending stress occurs at the mid span where the bending moment has its maximum value. So mb has pl by 4. Okay, this happens on the mid span in the sense somewhere over here. Okay, and you have to look up the formula of mb and see why does it act maximum over here and what is its value. Izz is clearly known for a beam like this, that is bh cube by 12, and sigma x max then can be found out because you have sigma x is equal to minus mb y by izz, so y has to be h by 2 or minus h by 2, and then you would have that. Similarly, tau xy max is something which you can find out by, sorry, this relation, this one, this relation. Okay, this will be maximum at what value of y, so that will be value at y equal to 0. So that will give you a ratio of this the desired ratio, which is the maximum shear stress divided by maximum normal stress in bending. Okay, and there are a lot of so I'll just go to that result and perhaps discuss, because this is very widely used. So tau xy max divided by sigma x max should be equal to half into h by L. Okay, so we already know what h is, that's the height of the beam, capital L is the length of the beam. Thus the bending and shear stresses are of comparable magnitude only when L and H are of the same height, same magnitude. So if L is much greater than H, do you see that tau xy, sorry, will be much smaller than sigma x max. Okay, so if it's a slender beam, then the shear stresses are negligible because the maximum value of the shear stress will be very small compared to the maximum value of shear stresses. So normally if the ratio is greater than 10 times, is L is greater than 10 times of H, then it will be or at least an order of magnitude smaller than the bending stresses. So if a different loading is put into the beam in figure 7.19, in this figure, the ratio of the maximum stress will again be found to depend on the ratio of the depth to the ratio of the beam. Okay, now in the sense, if this P was not acting over here but perhaps at some other phase, you would still have tau xy max by sigma x max as some ratio of h by L, not half. Okay, so you would still be able to make an approximation like this. Okay, so the factor of proportionality will not be half anymore. If beams of other cross sectional shape are investigated, similar results are applied. I mean, if it's not rectangular, say an I shape or an H shape, you will obtain similar result. Okay, so the factor of proportionality does however depend importantly on the shape of the section. So factor of half can be as large as 3 or 4 for I beams. Okay, so this factor of half can be like 3 or 4 times, and then you will have to reconsider this particular part, that if L is say 10 times greater than H, what would the other terms mean. Okay, so this is what we have for us in this class, and there is a small section on localized buckling in I-beams. We will not discuss it right now, it's one small paragraph, but it is in syllabus in this course, and you must do it after we have done with chapter 9, the last chapter. So you must come back to this later on. Thank you.